Now let's look into what are called as phasors. For that, we need to know that for a periodic signal, the complex Fourier series representation is going to be given in this form, where the time dependence of the periodic signal has been absorbed by this term e power j n omega naught t, and the coefficient of that term Vn, which in general is a complex number, Vn is a complex number, is what we call as a phasor. So that has both a magnitude and a phase. To understand what that phasor means, let's consider a single frequency periodic signal. For example, let the frequency be f, so the angle of frequency is 2 pi f. Then that periodic signal, let's say, is of the form of v naught cosine omega t plus phi, where this phi is in general an arbitrary phase. How does that signal look like? For example, if we were to plot it out, let's say the x-axis is the omega t axis, then this particular signal is going to look like perhaps something like this, where the cosine curve has been shifted to the left by an angle of phi, so this varies from plus v naught all the way to minus v naught being the amplitude, and this entire time period from one peak to the other is going to be t, and this frequency is 1 over t. Now for this signal, we can use the Euler identity that e power j theta is cos theta plus j sine theta. We can make use of the fact to understand and realize that e power j omega t is going to be cos omega t plus j sine omega t. If we were to make use of this fact, then we realize that e power j phi times e power j omega t is going to be e power j omega t plus phi, and I would end up getting cos omega t plus phi plus j sine omega t plus phi. So we got a term that looks very similar to here, that we see here, that term very similar here. We have obtained it, and that turns out to be the real part of this term here. That is the real part, and the imaginary part is being the sine. Now, meaning that I can write this expression as V naught times the real part of e power j phi times e power j omega t. And v naught being a real number, doesn't matter whether it is outside real or inside. I can always bring it back and write it as real part of v naught e power j phi e power j omega t. Now this particular term, which is a complex number having a certain magnitude and an angle, is what we call as the phasor, and let's say we denote it by a bar. So this bar, V bar, is going to be a phasor, and the time dependence is captured by e power j omega t. So this continuous time domain signal that is periodic is equivalently represented by a single complex number, what we call as the phasor. And for a complex number, we know that it has in the complex plane a real part and an imaginary part. In general, this V is going to be having a certain magnitude, and it is going to have a certain phase. In this case, that phase is corresponding to this phase angle of phi. So how do we see that pictorially then? What you see now is this phasor, which is independent of time. This is independent of time, a single number, but the time dependence of v of t has been captured by this term of e power j omega t. At t equal to 0, let's say at t equal to 0, we would have v of t equal to 0 is going to be simply a real part of v bar, since e power j omega 0 is going to be 1. So at that time instance, at t equal to 0, this is how the v of t is going to be looking at in the complex plane. Now, if as time progresses, this phasor starts to rotate in the complex plane. All the changes is this phase angle. The magnitude remains the same, but it is the phase angle that keeps changing. And that can be visually seen as omega t progresses, this phasor keeps circling around in time. And after beyond a certain time, it starts to repeat itself, which is basically the periodicity of the signal. It starts to repeat itself. And how often, how many times does it go around in 1 second is going to be the frequency. And the time taken for it to go one full circle, the time taken for it to go one full circle is going to be the time period t. Now, since we are taking the real part of the phasor times e power j omega t, since we are taking the real part, if we were to project this phasor to the real axis, this being the real axis and this being the imaginary axis, at any point of time, if we were to project it to the real axis, you recover back the periodic signal, as you can see in this animation. So a particular time snapshot of it is going to look like this, where this is the phasor, but at that particular time instant, if you project that to the real axis and get just the real part of it, and that real part is what is happening at that particular time instance of t. And taking the real part to recover v of t is just a convention. This is a popular convention, and there are people who use equivalently another convention to take the imaginary part of e power j omega t. In either case, v of t in this case is going to be, in reality, is going to be v naught cosine omega t plus certain phi, and in this case it's going to be v naught sine omega t plus phi. Be it cosine or sine, it's still a periodic function, but either convention is possible. Both conventions are being used. So in general, v bar is what is called as the phasor, and that phasor representation for a periodic signal of a certain frequency f, for a particular frequency f.